A single H100 GPU has 80 gigabytes of memory. A 1 trillion parameter model needs 2,000 gigabytes just to load. That's not tight. It's impossible on one machine. Google trains these models on 1,000 TPUs at once. Think of it like cooking a banquet for 300 million people on one kitchen counter. Here's the naive math. GPT-3 has 175 billion parameters. In FP16, that's 350 gigabytes. The biggest GPU holds 80. You're short by 270 gigabytes before training even starts. And even if it fit, one GPU crunching this data alone would take centuries to finish. The kitchen counter is nowhere near big enough. But weights aren't the whole story. Training needs gradients, optimizer states, and activations, leftover ingredients from every calculation. That adds up to 16 bytes per parameter, not 2. A trillion parameter model needs 16 terabytes just to train. This isn't a math problem anymore. It's an engineering crisis. Your first instinct, just add more GPUs. But naive data parallelism copies the entire model onto every single chip. Add 1,000 GPUs, each one still needs 2 terabytes. That's like opening 1,000 identical restaurant kitchens, each one too small for the recipe. More kitchens doesn't shrink the recipe. Here's what nobody tells you. Adding more chips doesn't automatically speed up training. Google's Palm run hit only 46% of theoretical peak compute. Meta's OPT run hit just 35%. Over half the hardware sits idle, waiting for chips to talk to each other. Communication, not compute, is the real enemy. The first fix, data parallelism. Split the training batch across chips, each gets a slice of examples, computes its own gradients. Then all reduce. Every chip shares gradients, sums them, updates in lockstep. It's identical restaurant branches, same full recipe, different customers, results combined each night. Data parallelism is the easy win, but it has a ceiling. Every chip still needs the full recipe loaded in memory. For a 175 billion parameter model, that's 350 gigabytes per chip. No GPU has that. Splitting the customers doesn't help if the recipe itself doesn't fit in the kitchen. So split the recipe itself. Tensor parallelism cuts a single giant weight matrix, say 12,288 by 12,288, into row chunks across chips. Each chip computes its slice of the multiplication, then combines results. It's 4 chefs sharing one giant wok, each stirring their own quarter simultaneously. But chefs sharing a wok need to stay close. Tensor parallelism demands blazing fast communication, NVLink or TPU interconnect, because chips constantly exchange partial results. Across 4 GPUs, that adds roughly 5% overhead. Across a slow network, it explodes. This only works inside one tight kitchen station. Next, pipeline parallelism. Instead of splitting one dish, split the courses. A 96-layer model gets carved into chunks, layers 0 to 23 on node 1, 24 to 47 on node 2, and so on. Data flows forward through the stations like an assembly line, then backward in reverse. Here's the catch. While node 4 cooks dessert, nodes 1 through 3 sit idle waiting. This is the pipeline bubble. Wasted chef hours. Naive pipelining can leave most of your assembly line doing nothing at any given moment, burning expensive compute time for zero output. The fix: micro-batching. Instead of sending one huge batch through the pipeline, send many tiny slices back to back. While Station 4 finishes dessert on Slice 1, Station 1 already starts appetizers on Slice 2. Google's Gpipe and Megatron's interleaving shrink the bubble to under 5%. Real training combines all three. Palm, Google's 540 billion parameter model, ran 12 data parallel replicas, 12-way tensor parallelism per node, and 8 pipeline stages. That's 1,152 slices total. Each of the 6,144 TPU chips held just 468 million parameters, a sliver of the full recipe. Why TPUs? A GPU is a general-purpose stove, great at everything, master of nothing. A TPU is custom silicon built for one job: matrix multiplication, the core of every neural network step. TPU v4 hits 275 teraflops on that one task, with an interconnect built to keep thousands of chips talking fast. That interconnect matters more than raw speed. TPU pods link 4,096 chips through a custom optical mesh at 1.6 terabits per second, all to all. Compare that to InfiniBand at 400 gigabits between nodes. It's chefs shouting across one open kitchen versus radioing between separate buildings. One more trick for memory: gradient checkpointing. Instead of storing every intermediate calculation from the forward pass, you throw most of it away and recompute it during the backward pass. This cuts activation memory by 10x. The cost, about 33% more compute. A classic time for space trade. Add mixed precision training, FP16 for speed, FP32 master weights for accuracy, and you get the full memory bill. A 1 trillion parameter model needs roughly 16 terabytes of state spread across chips holding 32 gigabytes each. That's at least 500 chips just to hold the recipe. Here's one training step on 1000 TPUs. Embeddings flow through pipeline stage 1, forward through 7 more stages. Backward pass reverses the flow. Then a 1000-way all-reduced syncs gradients across every data parallel replica. Each chip updates its own tiny shard. Repeat 780,000 times. This isn't theoretical. Google actually ran this. Palm 540 billion parameters, 6,144 TPU v4 chips split across 2 pods. Training took 78 straight days. Estimated cost, $9 to $15 million. And they still only hit 46.2% of peak compute. Proof, even Google fights the bottleneck. Here's the part tutorials skip. It breaks, constantly. Meta published their OPT-175B training logbook. 992 GPUs, 992 GPU days. It logged 35 outages and 4 hardware failures requiring manual restarts. Training a trillion parameter model isn't just math, it's a 24/7 operations war room. Compare the two approaches side by side. Google's TPU mesh hit 46% utilization. Meta's GPU cluster with InfiniBand hit only 35 to 40%. Custom silicon with a dedicated network beats general-purpose hardware stitched together, but it costs Google billions to build that kitchen. OpenAI won't confirm exact numbers, but estimates put GPT-4 at over 25,000 A100 GPUs, more than 90 days of training, and over $100 million in compute cost. Whatever the exact figure, nobody trains frontier models on a laptop. This is industrial-scale cooking. Watch the price tag climb. GPT-3 in 2020, about $4.6 million to train. Palm in 2022, $9 to $15 million. GPT-4, rumored, over $100 million. Every generation gets bigger, and every generation demands a bigger kitchen. More chips, more parallelism, more coordination. Let's map the whole kitchen. Data parallelism, identical restaurant branches serving different customers. Tensor parallelism, chefs sharing one giant wok, splitting a single dish. Pipeline parallelism, an assembly line of stations passing courses down. Combine all three, and you cook a meal too big for one kitchen. In your next system design interview, say exactly this. We can't fit the model on one device, so we combine data, tensor, and pipeline parallelism to shard both the batch and the model across the cluster. That sentence alone signals senior-level distributed systems thinking. This is also why transformer architecture looks the way it does. Attention layers and layer normalization are deliberately shaped to split cleanly across chips. Model design isn't just about accuracy anymore. It's co-designed with how well it shards. The math and the hardware evolve together. Where does this go next? Models keep growing past 1 trillion parameters. Google, Meta, and OpenAI are racing to build bigger pods, faster interconnects, smarter scheduling. The kitchen keeps expanding. Thousands of chips today, tens of thousands tomorrow. Compute is no longer the bottleneck. Coordination is. Here's the metric senior engineers actually watch. Model FLOP Utilization, or MFU. It's not about how many chips you have, it's how much of their theoretical power you actually use. Google hits 46%, Meta hits 37%. That gap is worth tens of millions in wasted compute. 3 things to remember. 1. Memory, not compute, is usually the first wall you hit. 2. Data, tensor, and pipeline parallelism solve 3 different problems. 3. Even at Google's scale, over half the hardware sits idle waiting on communication. Scale doesn't fix inefficiency, it just makes it pricier. Training a 1 trillion parameter model is cooking a banquet too big for one kitchen, so you split the recipe, clone the kitchen, and build an assembly line, all perfectly synced. Understand that, and you understand distributed training. Subscribe for the next deep dive into AI infrastructure.